Section 10.3.31-T, a math teacher claims that she has developed a review course that increases the scores of students on the math portion of a college entrance exam. Based on data from the administrator of the exam, scores are normally distributed with a mean which is equal to 515. The teacher obtains a random sample of 2,400 students, puts them through the review class, and finds that the mean math score of the 2,400 students is 520 with a standard deviation of 116. We're going to complete parts A through D below. So, in part A it says, state the null and the alternative hypothesis. And we're going to let mu be the mean score. Well, if you take a look at the beginning part of the sentence, okay, it says a math teacher claims. Okay, so claims, and we're talking about the mean being equal to 515. So we know that we're going to have a null hypothesis and the alternative hypothesis. Now the alternative is where you always see the claim. And the claim is saying that it increases the scores of the students on the math portion. So therefore, we're going to say in the claim or the alternative that mu is going to be greater than 515. And therefore, the null always has the equality, so mu is going to equal 515. Okay? So now that is step one of the null and the alternative. Now, if we move into part B, it says now, test the hypothesis at the significant level of 0.10. Is a mean math score of 520 statistically significantly higher than 515? So we know what our null and our alternative is. So we know that in step 2, if we continue from here, we know that it's going to be a right tail. Okay, and in number 3, we want to test the level of significance to be 0.10. Okay, and then number 4, okay, in the question it's saying that the mean math score is 520 with the 2,400 students. So we know that the sample mean is going to be 520. We know that the standard deviation is given to be 116. We know the value of n is going to be 2,400. And we also know that the claim mean is 515. So let's find the test statistic, which we know is going to equal 520 minus 515 divided by the standard deviation of 116 divided by the square root of 2,400. Okay, and so let's see what that approximately equals. So we take 520, subtract 515, and then we're going to divide that by 116 divided by the square root of 2,400. And so therefore, let's take a look at our test statistic. So if we round that to 2 decimal places, and we end up getting 2.11. Okay, let's take a look at step 5. Okay, we want to draw our bell curve. Okay, we know our mean is at 0. We know that our test statistic is located here at 2.11. And what we want to be able to do is find this p-value here. Okay, now we can find the p-value by using TCDF. Okay, we know that our lower value is 2.11. We know our upper bound is 9999. And what is the degrees of freedom? Well, the degrees of freedom is taking the sample size n and subtracting 1. So 2400 minus 1 is equal to 2399. Okay, so let's see what that p-value is going to be. So second distribution, we're going to go down to TCDF. We put in our test statistic of 2.11, going to 9999. We know our degrees of freedom is 2399. Select paste. And let's see what our p-value is. So here we can see that our p-value rounded to 3 decimal places is 0.17. So what does that tell us? So in conclusion, let's compare the p-value with the alpha. So if we take the p-value, round it to 3 decimal places, which is 0.017, okay, and the significance level is 0.10, so therefore this is less than 0.10. So since the p-value is less than the level of significance, then the sample mean is statistically significantly higher. Now, if we wanted to use this on a calculator using the t-test, let me show you how to do that. Okay, so we're going to come in here, open up the calculator. Okay, and we're going to go to Stat. We're going to go to Tests. We're going to go to t-test. Okay, and then we have the stats and not the data. And so we're going to put in the mean in our problem, which is 515. We know that our sample mean, which was given here, was 520. We know that our standard deviation was 116. And then we know that the sample size was 2400. And we know that the alternative had the greater than sign. So we want to go to the greater than sign and then select calculate. Okay. And so you can see here that with that information, that gives us the test statistic of 2.11, which is what we found here, and the p-value of 0.017. Okay, so let's go ahead and open up StatCrunch. So if we take a look at StatCrunch, we want to do the same thing. We're going to go to Stat, go all the way to T-Stats, go to one sample, and we're going to go with Summary since that's what we have. We don't have the data listed there. So with Summary, we're going to put in the sample mean. The sample mean that's given is 515. Excuse me, 520. We know that the sample standard deviation is 116. We know the sample size is 2400. And we know the hypothesis test for the null is equal to 515. And then this is going to be greater than 515. And then we're going to select compute. And then if you notice here, we're going to get the same result using StatCrunch. And so with StatCrunch, you can see we end up getting the test statistic to be 2.11, and there is the p-value. Okay, now let's move on to Part C. Okay, Part C says, do you think that a mean math score of 520 versus 515 will affect the decision of a school admissions administrator? In other words, does the increase in the score have any practical significance? Well, a good rule of thumb for determining the practical significance of a sample mean is to accept a difference of 5% or greater as a statistically significant. Now, the percent difference between 515 and 520 is about 1%. Thus, the sample mean is not practically significantly higher. Okay, let's go to Part D. In Part D, it says, test the hypothesis at the significant level of 0.10 with the sample size now at 400 students. and we're going to assume that the sample mean is still 520 and the sample standard deviation is still 116. Is a sample mean of 520 significantly more than 515? Okay, well, first and foremost, we still have the same null and the same alternative hypothesis. We still have a right tail, and we still know that the significance level is 0.10. Okay, so what do we know about step 4? Well, we know that the sample mean is still 520. We know that our standard deviation is at 116. We know that our claim value is 515. And now we know that the sample size is at 400. Okay, so now we're going to use our test statistic formula. So now we have 520 minus 515. We're going to divide that by the standard deviation of 116 divided by square root of 400. So let's go ahead and do that. So we got 520 minus 515, which is 5. We're going to divide that by 116 divided by the square root of 400. Okay, so here we get our value. If we round out to 2 decimal places, so now the test statistic is 0.86. Okay, so again, if we want to find the p-value, we're going to draw our bell curve. Okay, we know that we have a mean at 0. We know that our test statistic is 0.86. And now we want to be able to find that p-value. So we're looking for the area to the right to find that p-value. So remember that the p-value is going to equal TCDF. We know our lower limit is 0.86. We know our upper limit is 9999. And what are the degrees of freedom? Well, the degrees of freedom is taking the sample size and subtracting 1. Well, this is now 400 minus 1, which is equal to 399. So let's find the p-value there. So we're going to take second distribution, scroll all the way down to TCDF. We know our lower limit is 0.86. We know our upper limit is 9999. We know the degrees of freedom is 399. And let's select paste. And therefore, we're going to get our p-value. Okay, so if we round our p-value to 3 decimal places, we're going to get 0.195. Okay, now let's go ahead and compare the p-value with the significant level. We can see that the p-value is 0.195, and it is greater than the significant level of 0.10. So since 0.195 is greater than 0.10, the sample mean is not statistically significantly higher. Okay, now to make a conclusion about the effects of a large sample size, examine how the p-value changed when n increased. Large sample sizes can lead to results that are statistically significant, while the difference between the statistic and the parameter in the null hypothesis is not enough to be considered practically significant. So as n increases, the sample size increases, the likelihood of rejecting the null hypothesis increases. However, large samples tend to overemphasize practically insignificant differences. Okay. Now, the other thing is, for this last step, if we want to just get, again, using your technology here, if you wanted to do the t-test. So in here, if you want to use the calculator, we're going to go to second distribution. Sorry, you're going to go to stat, go to tests, go down to t-test. Okay, we have stats, We know that the mean is 520. We know the sample mean is 520, the mean is 515, standard deviation is 116, and then we're going to change the sample size now to 400. And then that remains the same, and then we're going to calculate, and then you can see that the t-test is going to give you the p-value and the test statistic here. And then if we wanted to use StatCrunch, then we would go to stat, we would go to t-stats, go to one sample, and that's going to be with summary. And we know that the sample mean is 520. We know the sample standard deviation is 116. Now the sample size changed to 400. We know that the mean is equal to 515. And we know that this is the greater than. And we select compute. And then if you notice here, again, down at the bottom right of the data information, using StatCrunch, you can see that we get the t-statistic of 0.86 and the p-value of 0.195.